6.3, a vector. A vector is a quantity or directed distance that has both magnitude and direction. So a vector is represented geometrically by a directed line segment. So I need to point something out to you. We will call this vector V. Now it looks like a ray, but I need to distinguish for you. We draw it like a ray, however, it's different from a ray in that it isn't continuing to go. It has a start and a stop. But we need to put the arrow that says what's the direction, because a vector has both magnitude and direction. Let me say that again. The reason why I have the arrow is this does not mean it goes forever. That's just telling me the direction it's going. There is a start and a stop. A directed line segment that has an initial point, say P, and a terminal point, say Q, then PQ is a directed line segment. So let me draw a picture here. So here's P. Q is really that terminal point. It's the stop. But we do write it, and we write it, it does look like a ray symbol above it. Its magnitude or length is denoted by, and it looks like absolute values. And I want to point this out. Today you're going to get a lot of vocabulary. It's going to be a little bit of an overload for you. And you're going to want to take time and read through your notes, reread your notes, maybe even twice, to try to get all the vocabulary down. Magnitude in physics is another way to say length. Okay? All right, two directed line segments that have the same magnitude and direction are equivalent. So we would say vector U is equal to vector V, and I'll do my best to draw this. If this is vector U, V has the same direction and the same length or magnitude. Example 1 says, let U be represented by the directed line segment from P is 0, 0 to Q is 3, 2. And let vector V, and I want you to notice that in your textbook and in these notes, a bold letter indicates a vector. I couldn't get the little arrows above it. Now I actually did figure out how to do it, but I already had this in my smartboard. So here we go. Let's make a sketch. So the nice thing is you're using a coordinate grid like you use a coordinate grid. So P starts at 0, 0, and Q is 3, 2. But because the initial point is P, the terminal point, terminal meaning stop, is at Q. Notice it looks like a ray, but there really is a stopping point. Then it says I've got vector V is from R is 1, 2 to S 4, 4. So let's go 1, 2. We'll call that R. S is 4, 4. It says show that vector U is equal to vector V. Well, let's pause here a moment. What is a vector? It's what? What? I mean, it's a directed line segment that has magnitude and length, or magnitude and direction. So how can I show that these two vectors are equal? Okay, if they have the same magnitude and direction. All right, well, what's another word for magnitude? Length. Oh, what tool is in our tool belt for length? Distance formula. There we go. So magnitude, let's pull the tool out. If I want the magnitude, they use these like parallel lines, almost looks like it's absolute value, but I can use the distance formula. 3 minus 0 squared plus 2 minus 0 squared. Now that you're pre-calc students, we can, do a lot in our heads here. Wouldn't that be 3 squared plus 2 squared? 9 plus 4, that's the square root of 13. And then I want to do the magnitude or distance of RS. Well, that's 4 minus 1 squared plus 4 minus 2 squared. That's the square root of 3 squared plus 2 squared. That's 9 plus 4. All right, their magnitudes are the same, and you do want to, when we're talking vectors, we want to use the word magnitude, even though we're going to make a connection that really means length. Okay, so that shows the magnitudes are the same. The second thing we said we need is that the direction is the same. How do I show it? It looks like it, but that's not proof.
The slope?
Good job. It's the slope. Their slopes would be the same. So now watch this. I'm going to use a subscript because we're going to do two different slopes. So let's use slope subscript PQ. Well, we know y2 minus y1 over x2 minus x1. That's 2/3. And then we want to do the slope of RS. Again, y2 minus y1 over x2 minus x1. Now what I would like you to do, okay, we're now approaching, the closer to the end of the third quarter this year, and you're honors pre-calculus students. What you should be able to do if you're asked to show something's true, okay, we've done all the work, but now we should be able to kind of write a sentence that summarizes how do we know they're equivalent. Very straightforward, but what should we write down? This is how do we know this? How do we know the two are equal? Okay, all you need to say is vector u is equal to vector v because they have the same direction and magnitude. You did it. But you should be able to articulate or summarize what you did. So make sure when you're asked to show or prove, you're making some kind of a statement. And as the year progresses, now I'm going to be, rising with my expectations here of how you're going to do things. Okay? All right, another definition. A vector in standard position is a directed line segment whose initial point is the origin. So vector PQ is in standard position. What we're going to find out in a moment is there's a way to convert RS, vector RS, into this standard position. A vector whose initial point is the origin and can be uniquely represented by the coordinates of its terminal point, say v sub 1 comma v sub 2, this is called component form. And the way that you're going to write component form is like this. This is going to be new notation for us. It's almost like they look like V's. It's not a parenthesis, it's not a bracket, but this is called vector notation for component form. So vector PQ is written as 3 comma 2, and that's component form because it started at 0, 0. So let me say this again. When it's in this component form, it's assumed the initial point is the origin, and what you have here are your terminal values, okay? All right, the coordinates v sub 1 and v sub 2 are the components of v. If both the initial point and the terminal point lie at the origin, vector v is called the 0 vector. And it's denoted like this, and it's usually bold, but I don't know how to make bold, if we're just darkening it in. But the component form would be 0 comma 0. All right, the next definition, the component form of the vector with initial point P, which is P sub 1, P sub 2, and terminal point Q is Q sub 1, q sub 2, I can actually convert it into component form by subtracting the terminal point. Sorry. So you would take q sub 1 minus p sub 1, comma, q sub 2 minus p sub 2. And when you subtract, it's going to give you a component value v sub 1, comma, v sub 2. So, if you think about it, I could take rs and we can convert that into component form. That was 4 minus 1, comma, 4 minus 2. Notice that PQ had the same component form. That would eventually be another way to show the two vectors are equivalent. All right, magnitude or length of a vector v is just the square root of, depending on what form you have, oops, that's a 1. If it's not in component form, you would subtract, or you could convert it into component form first. And it would be the square root of v sub 1 squared plus v sub 2 squared. If the magnitude of vector v is 1, v is called a unit vector. We're going to use that in the next section. So for now, I just need you to understand a unit vector has a magnitude of 1. If the magnitude is 0, that's true if and only if it's the 0 vector, and we'll use 0 with the vector symbol. All right, two vectors are equal if and only if the first values are equal and the second values are equal. So again, what I mentioned just a moment ago is that now we could have shown that u and v are equal using this component form, which I'm going to do right now. Vector u is from p to q. So that's 3 minus 0, comma, 2 minus 0. So that's 3, comma, 2. Vector v is the vector from r to s. So those are equal. And clearly that's a much easier way to go. In example 3, it says find the component form and magnitude of the vector that has initial point 1, 11 and terminal point 9, 3. All right, component form means, okay, this is new vocabulary for us. We just defined it. Component form means that you're taking the vector and you're sliding it so its initial point is at the origin. So what I need to do is I need to take the terminal point minus the initial. So it's 9 minus 1, comma, 3 minus 11. So this is 8, comma, negative 8. So that's the component form for vector v. And then if I want the magnitude, it's much easier to use the component form than to do this stuff. So you're going to take 8 squared plus negative 8 squared. So that's 64 plus 64. And I want to pause here a moment and point out something that would be very, very helpful if you recognize it here, do you notice that you have two sets of 64? And when we simplify radicals, I don't want you to go on autopilot where you're just doing the work. You need to sort of stop and think about this. So when I have the square root of 128, and we will always simplify our radicals, but I had two sets of 64. So that simplifies to 8 radical 2. So if you ever notice that, you're taking the same number and adding it, you have two groups of them. Okay, and it makes your life a whole lot easier. And something I want to point out while we're here, just to make sort of a rough sketch, if I went right 8 and down 8, this is now been the vector that's been slid to the origin. So it was somewhere else, right? 1, 11 up here, and it was going like this. So they're really parallel. But I took it so that the initial point is now 0, 0. All right, there are two basic operations with vectors. They're not the only operations, but these are two basic operations. You have something called scalar multiplication and vector addition, both of which are very, very easy. In operations with vectors, numbers are usually referred to as scalars. Scalars are always real numbers. Geometrically, the product of a vector and a scalar is the vector that is the absolute value of k times as long as v. If k is positive, k times v has the same direction as vector v. If k is negative, then k times v has the direction opposite that of vector v. So I want you to make, it'll look similar to the music staff. Is that what you call it, I think?
Yes.
Okay. Does it have 5 lines?
Yes.
4 spaces? Okay.
Yes, it does.
So we're going to tie some music in here. Do some music. Here we go. All right, so let's say I have vector v, and I'm going to make it 1 space. If I want 2 times vector v, okay, so 2 is the scalar, 2 is a real number. What it's going to do is we're going to pretend that I'm doing this with the same direction. So it has the same slope, but it's twice the length. Now what if I have negative 3 times vector v? I do need it to go at the same angle, 3 spaces, but a negative makes it reverse direction. Okay, so scalar multiplication is super easy. Any questions on that? All right, now we're going to talk about vector addition and subtraction. I need you to open your textbooks to page 513. Open your books to page 513. And you're going to need your books open for a little while. It says to add 2 vectors geometrically, you position them without changing length or direction so that the initial point of one coincides with the terminal point of the other. So I want you to look on page 513 in the middle. Do you see on the left there's a vector u and a vector v? On the right side, here's what you do. If you want to take vector u plus vector v, you start with vector u, which they have, it's in the light gray, and then they took vector v and they put vector v's initial point at the terminal point, the ending point of u. And if you can imagine then, in red dash, they have a parallelogram. And so the diagonal is equal to vector u plus v. And that's called the Parallelogram Law. That's one way to do this, is you can do it geometrically this way. U plus V is also called the resultant vector. And next year, if you take physics, this will make a lot more sense as you get into the physics aspect. I'm going to show you a second way to do it, and this is the way I prefer to do it, is if you know the components, if vector U is U sub 1, comma U sub 2, vector V is V sub 1, comma V sub 2, then all you do to add the vectors is you add like what's considered to be in the first component plus what's in the second component. And if you subtract, you just subtract the components. So let's look at example 4. It says let vector V be negative 2, comma 5 and vector W be 3, comma 4. It says find each of the following vectors. Now this is a scalar, and I want to point out that in this lesson we don't do vector multiplication. That's different. It's not what you think. It's not intuitive. In 6.4 we will do vector multiplication, but this is called scalar multiplication. So I'm going to take 2 times the vector V. Well, this is super easy. It's negative 4, comma 10, and that should make sense. It's twice as long. Now if you do vector W minus vector V, this is 3, comma 4 minus negative 2, comma 5. Just be careful with your minus sign. This is 3 minus negative 2, so that becomes 3 plus 2, which is 5. And I take 4 minus 5, which is negative 1. All right, try letter C now on your own. This is very, very simple stuff. I would recommend when you're doing this one, I know some of you can do great mental work, but be careful with it so that you don't do something silly. I would go ahead and take a moment and do the scalar multiplication. 2 times W would be 6 times 8, and then add them, because you'd hate to lose some silly points because you did something in your head wrong, okay? Alright, any questions on scalar multiplication or addition or subtraction of vectors? Pretty straightforward. Alright, turn in your book now to page 515. We're not going to actually fill this out because I don't think we need to. But what the table's telling you, that blue table on the top of page 515, number 1 is saying that vector addition is commutative. Number 2 is saying vector addition is associative. Number 3, that's saying you have the additive property identity, the additive identity, that vector U plus the 0 vector is still U. Number 4 is the additive inverse property. U plus the opposite of U is 0. 5 is the associative property for scalars. Notice none of this is vector multiplication, because then that's a whole different ballgame. Number 6 is the distributive property, and so is 7. Number 8 is your identities. And number 9 is saying you can take the magnitude of the scalar times the magnitude of the vector, and they're the same. Okay, so you don't need to really fill that out. All right, in many applications of vectors, it is useful to find a unit vector that has the same direction as a given non-zero vector v. To do this, you can divide v by its magnitude to obtain the unit vector. So it says you're going to take vector v divided by its magnitude. It says, note, vector u, is really a scalar multiple of vector v. And let me show you how. Magnitude is a number, right? Magnitude is some distance. It's a scalar. It's not a vector anymore. So watch what I can do. I can factor and put 1 over the magnitude times vector v So do you see vector u is a scalar multiple of vector v? That's what that means. The vector u has a magnitude of 1 in the same direction as vector v. So the vector u is called a unit vector in the direction of v. And we'll see why we want to do this in the next section. In example 5, it says find a unit vector in the direction of vector v, which is negative 2, 5, and verify that the result has magnitude 1. Okay, well, a unit vector, start over here. A unit vector is equal to the given vector divided by its magnitude. Okay, that's the definition. A unit vector is vector v divided by the magnitude of vector v. So let's first of all find the magnitude of vector v. So this will be the square root of negative 2 squared plus 5 squared. That's the square root of 29. So my unit vector is negative 2, 5 divided by the square root of 29. So that's actually a scalar multiplication. So I can multiply each component by 1 over square root 29. Good news, I'm not going to make you rationalize. If in the back of the book they did, I know you guys can check it and just mark them correct. So there's your unit vector. Now, a unit vector means it has a magnitude of 1. And it says, let's verify that it has magnitude 1. So if I want to find the magnitude of this unit vector, so there was a very good reason why I didn't want you to rationalize it. It's going to be so much easier to do if it's not rationalized. It's really horrible if you do. The other thing is, in AP Calculus, most of the time you don't need to rationalize. You do need to know how to do it, because if their answer is rationalized, you need to know how they got to it. But sometimes, and on the free response section of the AP exam, you can leave them any which way you like. It doesn't matter. So we're going to start relaxing that here towards the end of our year. So now if I square that, that's 4 over 29 plus 25 over 29. 29 over 29 is 1. So we have just verified that it in fact has a magnitude of 1, which we said it did. All right, example 6 is the exact same type of problem. What I want you to do is I'm going to give you a head start. It says find a unit vector in the direction of 5, negative 12 and verify that the result has magnitude 1. So let's see if you can do this. Bless you. Oops, it's not a 15. understand why you divide by the 13? It is multiplying by 1 over 13. So it's just scalar multiplication there. And don't do a fudge factor, okay, where you know it's supposed to be 1 but you don't know how to really get there. Don't do that. Make sure you have enough evidence that supports how you would get it. Okay, any questions on that? Getting the unit vector. So remember, the definition of a unit vector is the given vector divided by its magnitude. Very simple. We'll figure out why we want to do that in the next lesson. All right, then go ahead and fill in the next couple of definitions, and then we're going to stop there today.